lot of great talks happening in parallel, so thank you very much for coming to this one. This one is a little bit different because we'll be talking a lot about hardware, and I appreciate this is a big software conference. But, you know, it's also called Build Stuff, so I thought it would be cool to talk about building tangible stuff. And what's also cool is that, unlike software, when you're angry, you can't really do much to a computer, but if you're developing circuit boards, well, you can do a lot of things to non-working circuit boards. Let's leave it at that. So, also thanks for Naringa and the crew for inviting me. It's my second time at Build Stuff. It's one of the coolest conferences around. Have you seen the duck? Like, what's up with that? So, hardware is fun, and you know, a lot of people are getting into hardware these days because it's so easy to do hardware. But shipping hardware is still a bit of a mysterious subject, so we'll try to talk a bit about that today. Logistics-wise, we have some system set up over there for questions, and I'll try to create some time at the end of the talk for some questions as well. But, you know, I'm around, or you can ping me on Twitter and we can have a chat afterwards as well. So, my name is Omer. I'm the CTO at Den, a hardware startup, an IoT startup in London. I'm an embedded systems engineer leaning towards more electronics than software, and hardware as well, of course. My homepage, you know, in 2017 we don't really have those anymore, but like my homepage is this, so, you know, click on it. This talk is about the process of shipping hardware products. So when I built the first version of the slide deck, I really focused hard on the process, and you know, it was a lot of acronyms and a lot of, you know, diagrams and stuff like that. But I was rehearsing on the plane yesterday, and silently, and I realized that it was actually just too many slides, and not just too many slides, but it was a lot of text. So I arrived at the hotel at midnight and said, okay, I'll change a few things, and by 3:30 I changed 75% of the slides. So this is the first time I'm like publicly giving this deck, so you know, it will be fun. So again, you know, this talk is about shipping hardware products, but I'm gonna talk about 4 subjects. So the first one is hardware landscape, and why is it actually fun to be doing hardware in 2017? And the second one is just a very high-level overview of what it takes to ship a hardware product, or not just shipping perhaps, but more focusing on the development side of things. What does it take to develop a hardware product? And you know, since I don't want to disappoint you because the abstract says process, we'll look at one example of a formalized process for product development. Now, product development differs greatly from, you know, hardware development because it's not just the hardware alone, right? It is everything surrounding the hardware and, you know, coupled with marketing, research, you know, all those other activities as well. Just to clarify, this talk is focusing on the development side of things, and particularly on the electronic side of things. And you know, we're not going to be talking about how to do market research. We're not going to be talking about how to like pitch to IoT accelerators or whatever. If you want to have a chat about those, I'm happy to do so later. But in this deck, we'll talk about hardware development, and we'll have a lot of shiny pictures in a bit. The bit that I started adding last night was actually a case study, because you know, we can talk about process all day long, and you know, you'll need a lot of coffee and perhaps stronger liquor later. But if you talk about an actual product, and if you try to apply a formalized process to it, I thought it would be more fun. So I dug out like a project I did a few years ago, and we're going to go through that and look at the different stages of development for that. So there's a lot of references, links, and generally a lot of stuff on the slides. So if you want to grab a copy of the slides, this will be the URL for it. I'm sure it will be distributed on the website later as well. And while we're waiting for that, let's do a quick show of hands, or while we're waiting for people to type or take photos, hands up or raise your hands if you're a software developer interested in hardware. That's great. Hands up if you own a Raspberry Pi or an Arduino. Wow, great. And also finally, hands up interested in designing, if you're interested in designing and shipping a custom hardware product. Cool. Right, so let's get into it. Let's start with the As a hardware engineer, I have a very strong, or I have mixed feelings about the statement hardware is easy. I mean, yes, it is easy to prototype these days, right? I'm sure most of you, or some of you might have these on your desk. You might have a couple of Raspberry Pis deployed in your home. You deployed a year or two ago and you don't know what it does anymore. It's probably a botnet by now. But these things are ubiquitous and these things are cheap. You can get a development board for, well, actually they'll throw them at you for free. But if you want to buy them, they're like nothing really. So yeah, prototyping with hardware is easy, and really, you could do some very cool stuff with, the existing hardware projects. And some of these happen to be open source hardware as well, so you can actually base your products on them as well. It's a great learning experience, and even in large corporations, when I have discussions with engineers working in research labs, everything starts off as an Arduino or a Raspberry Pi prototype these days. So yeah, so hardware is easy in that regard. Prototyping is super easy. And my favorite website is AliExpress. And you can buy 45 sensor modules shipped from China for $16. I mean, yes, hardware is easy if you look at it this way, right? And the seller will also point out that 45 in 1 is better than 37 in 1. Depends on what context, obviously. But in this one, the math checks out. So yeah, if you combine a Raspberry Pi with or like an Arduino with a temperature sensor, yeah, you'll have your next IoT, whatever enabled thermometer. But, if you're thinking of manufacturing with, say, like a Raspberry Pi based project, then go and talk to Broadcom and see if they will sell you some chips. They won't. Also, like manufacturing with these things are, it's not really getting easy. It's getting harder, if anything, right? So on the left here, what you have is the PCB footprint for the processor on the Raspberry Pi. And each one of these tiny dots is a joint, is a leg, is a connection, right? And what's more interesting is that if you look at the Raspberry Pi, the original one, and the Zero, the RAM is actually soldered on top of the processor, which is then soldered on there. I mean, the ordering is different, but it's a fairly complex process. It's called POP, package on package technology. And what I was saying earlier, again, try and buy a Broadcom like BCM 2835 or 36 or 37. They're not going to sell it to you. I took this picture. These are some Qualcomm chips that I bought from a market seller in Shenzhen. And, it was incredibly easy. I went there, I said, do you have this chip? Yes, I have this chip. It will cost you $2 each. Thank you very much. That was it. Whereas you try calling up Qualcomm in UK, they're like, I don't know if I should be disclosing it, but it's too early for lawyers anyway. So they're like, oh, unless you can commit to 250,000 units per annum, it's not going to happen. The conversation is not going to happen. And what's worse is that these chips the chips that we have, the processing devices that we have are very, very complex devices. They have a lot of moving parts and they have calibration requirements if you have a radio and stuff. You're not going to get the information from, MediaTek about how to calibrate their Wi-Fi radios. It's just very difficult to do so. So again, hardware is easy if you're prototyping or, just tinkering. But manufacturing is still very difficult. But I don't want to be negative, so there's also some really positive stuff happening in terms of manufacturing. Desktop manufacturing, right? You probably have, hands up if you have a 3D printer or played with one before, right? So 3D printers are becoming more ubiquitous and they're getting really good as well. So, if you don't live in a tiny flat in London, if you have a bit more space than I do, you probably can, put your own 3D printer, little CNC mill or little circuit board, printing station / pick and place on your desk and have like a mini factory on your table. How awesome is that, right? You don't even need to leave your study. You could be in your boxer shorts and be manufacturing stuff. Like that is very cool. So, and if you can't be bothered with that, of course, there are services aimed at makers or prosumers that will produce PCBs for you for not that much money or 3D print plastics for you. It's good. But, still, you need to take the whole pontification or thought leadership of hardware is easy with a pinch of salt, because it depends on the context that you're evaluating the statement in. So looking at the hardware development lifecycle, this actually doesn't differ that much from software, right? So you have specifications, you hack together a proof of concept, and then you do some serious engineering, and then you end up going through different rounds of prototypes, and then you end up with a product. So if you look at it at the highest level, hardware development is very similar to software. Now the main differentiators are costs and timelines, because it could take 8 to 10 weeks for a tool to be made for you to produce plastic parts. Like, it could literally take months to get the tooling ready to bash out a lot of these parts. Once the tool is ready, you can do thousands in a week, but getting there takes a lot of time. And also, iteration cycles are very, very slow. We'll touch that in a bit, but if you have a 2-week iteration cycle as opposed to being able to deploy a new feature, and do get super nice tooling with like you do in software projects, you don't have that in hardware, so things become quite difficult to manage. So generally, you end up with a lot of hair, and then towards the end of the project, you end up with, not that much hair. So again, I was going through, the manufacturing books and resources and stuff, and I ended up stumbling across this simplified, kind of illustrated guide to product development. It's a blog post by a hardware VC. The guy who did it, Ben Einstein, he has an incredible Twitter account, and he does a lot of teardowns of products and stuff. So I highly recommend you go and check out the link, because they have some really solid stuff in there. So I know this is a lot of stuff and it's a big room and so on, so we'll break this down in the next couple of slides. But primarily what we're concerned about is how they break this down into main activities. So they do it by creating 4 kind of tracks of activity: ideation, design, engineering, and validation. Let's go over them one by one. So in the first phase, and you'll see the parallels of this to the software side of things as well. It will start differing towards the tail end when we're talking about manufacturing. You need to figure out what it is that you want to manufacture, right? So you might have a great idea, but you need to do market validation to see if the world needs, say, a Bluetooth-enabled toothbrush that is a real product. You need to put together some, prototypes, another prototype perhaps with a proof of concept to demonstrate what it is that you're trying to sell. And, it is crucial that you actually end up, you figure out what it is that you're trying to sell, and you validate that idea very quickly, because, the hardware startup world, especially in the era of Kickstarter and so on, it's filled with all these really random hardware products that seemingly, exist, but for what reason, nobody really knows why. So, what this talk is about engineering, so let's focus on that. So the ideation phase is the first one. It kicks off the whole, development by ultimately defining what it is that we're trying to build. Next stage is design. Again, we'll kind of briefly go over this. We want to focus on the blue track and the green track over there. This is again iterating through, the customer feedback that you're getting. If you have an app, let's face it, everything has an app these days. You wireframe that. You have different prototypes. Again, you get user feedback, and it's really important to try and get the whole looks like, works like, concept kind of integrated into your development flow early on, because nothing beats, getting real feedback on a real device, even though it's mocked. Like, everything might be mocked. Backend might not exist. Everything might be hard-coded. But it's still very good to see user feedback, when you actually have, people that will give you honest and true feedback. Again, moving on to engineering, because we're going to focus on that mainly. It all starts with a specification. Now, everybody hates specifications. Nobody likes documentation, let's be real. But it's crucial, because it's not only, this does this. It is, in terms of hardware, you set certain things in there that ultimately affects the whole development really, really deeply. So an example to this is target cost. So if you know that the product that you're developing needs to sell for X, right? You can, through some math and research and a bit of a hunch as well, you can say, okay, I can dedicate 20% of that to be the actual circuit board assembly cost, right? And working backwards, if you know that you can only dedicate, say, X, divided by 4 or 5, 20, 25%, whatever, then you can say, okay, I know the circuit board is going to take up this much of that. That means I have like $1 for the processor. And that kind of sets the limit as to what sort of processor you're going to go with, right? For $1 you can get a lot of processing power these days, but you're probably not going to get a multi-core device, right? So specification is not just simply about, okay, we're going to use these batteries, whatever, but it's also trying to get a bigger picture understanding of, ultimately how much freedom you have in choosing parts. So this is a tough one because, especially if you're doing this for the first time, the whole target price, target costing, if you look at how much you actually need to dedicate for marketing, for instance, it's actually, as an engineer, it makes me angry, but that's the reality of the thing, right? So, and there will be cases where, oh, you have like 8 megabytes of flash. Why do you need more? Because it's 2017 and everybody uses abstractions and JavaScript. So, the next stage after that, of course, is the validation. And this is where things start kind of differing a little bit from software projects. Because once you have the engineering prototype, you're actually at a stage where you can start engaging with contract manufacturers or contract electronics manufacturers. So depending on volume and scale and obviously your project, what sort of technologies you need and use and so on, you're probably going to end up working with a manufacturing partner unless you're doing a super niche thing that you can just manufacture using a beautiful 3D printer, etc. in your room. Now that's a valid application. There are cases where, especially in, say, like music or guitar pedals and stuff, there are people who are doing super specialized things. It is technically a manufacturing operation. They're probably producing maybe 10, 15 off something. But in that case, the manufacturing operation can be set up in your garage or even your study. But in most cases, medium to high volume manufacturing, you're going to be interfacing with, somebody that does this for a living. And, they have assembly lines, they have workers. And that comes with processes and, all these very rigid hierarchies. So at this point, I'm going to sidestep a little bit and say, this is obviously a very simplified view of the entire subject because, the entire process depends on so many actors and there's real costs associated with it. Tesla is not going to be using this process, let's put it that way, right? But this is more geared towards startups or perhaps people who are just starting out in the hardware game because if you look at a real hardcore, engineering, hardware lifecycle, whatever management process, it is big, it's scary. But this, for all intents and purposes, will cover pretty much all the key areas that you need to focus on if you're just starting out on this. Now there are different stages, and again, there's a lot of acronyms. We'll try to cover all of them. EVT, DVT, these are different phases and they also have a lot of different names. But effectively what happens is you have your engineering prototype. It kind of looks like and works like, the device that you want manufactured. But there's a whole bunch of stuff you need to do before you can actually get to that point, right? So designing one-off prototype, is super easy. Again, this goes back to the whole hardware easy thing. But then going through the DFM, design for manufacturability or design for manufacturing activities, is actually where, the secret sauce is. I hate myself for using that, sorry. So, ultimately it is about making sure your design can be multiplied, 1,000 times or 1,000,000 times. And that's where things get interesting because like one component that you picked widely available from distributors, if you want to buy, say, I don't know, 10,000 of them, they might say, okay, well, you have a 52-week lead time, or you need to wait 52 weeks to receive this many parts. So what do you do then? Do you delay the project by 52 weeks? We'll talk about component choice in a bit, but the point is that the entire process revolves around going from one-off prototype or a couple of prototypes and going through different stages of validation to ensure that you have a manufacturable design. And not just the design files themselves, but the process of testing, assembling, and shipping and all those kind of things need to be validated as part of these processes as well. And then at the end of the road, you have mass production. At that point, everything should be, good to go into scale, but it always is not the case. So let's switch over to some pretty pictures. And the example project we're going to look at is a little attendance monitor I did a few years ago. It's one of the projects that I'm not bound by NDAs and I can talk openly about. It's not the most complicated project. The idea is that at a university you have attendance sheets, but as we all know, everybody signs for each other and they're basically useless. And some poor admin person needs to go and enter those things into a system. So we realized that, well, actually the cards that people have or should have in their pockets all have RFID chips in them. So why don't we design a device that utilizes that and just takes away the whole burden of admin and people signing for each other, until they figure out how they can clone student IDs. So volume-wise, this wasn't a massive project. It was only a couple of hundred units. But it was at a scale where we couldn't manufacture this ourselves. We had technicians and we had facilities, but it was kind of just over the amount that would have been comfortable or feasible to manufacture with our own resources. So we ended up working with in this case, a local contract electronics manufacturer. And budget was not that great, and I'm sure you're familiar with this as well. So let's start with, let's go back to actually the whole simplified, product development or hardware development flow. At the beginning of the road, we interviewed a lot of people dealing with this data entry and so on. We talked to students, we talked to lecturers, we talked to all the users of the system to get a sense of what is actually the problem and what sort of a device do we need to design to fix this problem. And then we capture that in a functional spec. Now, again, nobody likes documentation, but if you're serious about developing hardware, I can't stress the importance of just taking notes. They don't need to look pretty. They could just be in a logbook or whatever, but you need to trace your steps. And if you're doing a commercial project especially, you really need to keep track of all the technical decisions and why you've decided to do them or decided to take them. So once we had a functional spec, we were at a point where we could validate this idea quickly. The feasibility of actually using the student IDs to see if we can make them work with our little reader chips or reader modules that I got. So I built this monstrosity on a breadboard. Took me a weekend to build it. And as you can see, it doesn't look like a finished circuit board. It is just a bunch of things that are wired together. The battery is meant to go in that little red module over there. It's not just there for show. So the battery connects there. That's the power section. That's the microcontroller. There's I think it's I2C memory somewhere here. I can see the I2C SDA and SCL lines. This was an accelerometer module. We decided not to use it because of cost reasons. And the RFID module is buried over there, and an external antenna was connected to that so that we can see it. The purpose of this was to, again, validate the idea from a technical standpoint and to see if we can actually produce a device like this with a sensible budget. And it turns out that, with a couple of substitutes and by ditching some features, again, that's why this guy is not connected to anything, because it was quite an expensive chip. it turned out that this is technically sound and feasible. So we reached a point where we had a works-like prototype. A works-like prototype, as the name suggests, should work like the final product that you're trying to develop, but it doesn't necessarily need to be in the same shape, same form. Depending on what sort of team you have, at this point you might want to bring industrial designers in to design the first iteration of the case. If you have access to quick prototyping facilities, you might just bash out a small PCB to fit in there to see how it's going to work and so on. In this instance, I know nothing about mechanical engineering, so in this instance I was focusing purely on the electronic side of things, and having that prototype also meant that I could start with the next stage of activities, which was firmware and software stack. So there are lots of arrows, and this thing, the problem with this is that all of these things happen concurrently and in parallel, and there's quite a bit of a mishmash of activities affecting each other as well. This doesn't show you the dependencies very well. But you can see that the idea might change, the problem might change the direction of the prototype that you're building. So it's quite iterative. There's quite a few cycles of this process you have to go through before you have the final product definition, most definitely the final product. But again, building this breadboard allowed me to start the firmware development. It allowed the technical team or the sales or marketing, internal sales and marketing, to start pitching the idea to people, to gauge demand, what sort of volumes we needed to produce this in, and so on. So this was kind of a big milestone in which we said, okay, we're doing this now. This makes sense. After that, the real engineering starts because you're not gonna give the breadboard to somebody and say, make me a lot of these. You can. There are consultants that will do it for you. But I'm a hardware engineer. It's not fun. So the next stage is actually going from that messy, breadboard prototype to capturing the schematic, which is a visual representation of what that circuit was doing, into the circuit layout, which is the physical footprints that the silicon chips will sit on and be soldered to and be connected. If you watch like terrible low budget movies, you'll see circuit boards, things flying in circuit boards. That's circuit boards. Effectively, those are copper traces connecting silicon parts. This is a crystal. This is a microcontroller. This is another crystal. It's just electrical connections represented in the schematic sheet, just transferred to real copper tracks. More on this in a second. So this is all fine, but at this point we're getting serious. So we also need to start thinking about how it is that these things are going to be manufactured, right? So again, if you're producing 15 of something, you don't need to really worry about what components you use, because you can hand solder them, you can snip them, you can file them. You probably have a huge profit margin to warrant your efforts to, for you to do those things. But if you're trying to produce something in the range of thousands, then you probably want to automate this as much as possible. And that's where, and we're going to talk about components now, that's where surface mount technology comes in. Surface mount literally means that these things don't have any legs poking through the board that needs to be soldered manually. Now, through-hole soldering can be automated as well, but it's quite messy. So surface mount technology is great because these components can be picked up by beautiful machines called pick-and-place robots, and just placed on the patterns where you might have some solder paste already laid out using a stencil process. And if you can have 100% surface mount circuit board, then it can be scaled, obviously within reason, quite well. I was going to say infinitely, but never use the word infinite in engineering context. So the way the automation works is that these reels contain all the components. So this middle one, for instance, is some capacitors. This could be resistors. And these reels get loaded into these beautiful pick-and-place machines. And then these things have suction cups that go and just place things on board. No human interaction necessary. Well, the humans program the robots to do these things. They're not sentient yet. But ultimately, once the programming is done, you could just put a board in, it will populate it for you, and then it can go into being soldered. Now, not everything can be, on a reel. There are certain packages or modules you might use that may come in trays. These are called waffle trays. And some chips, some larger chips, come in these waffle trays that are placed near the machine's receptacles, and then the suction cup comes down, picks them up, and puts them on the board. Selecting components is actually quite critical, and there are quite a few parameters you need to pay attention to, even when you're picking the simplest microcontroller. Packaging, we just covered that. Surface mount, good. Through hole, not so much. But you might be restricted as to what you can use, because a part might only come in a through hole package, or it might come in a very complex BGA ball grid array package or something like that. MOQ, another acronym, minimum order quantity. So if you're producing 200 of something, but you can only buy a full reel, like 5,000 of this part, then it's a huge cost, right? Usually you could just go to a distributor and then just buy 200 plus the error margin quantity, but obviously the distributor will put their own margin on top of that, and this gets quite tricky. Quantities around 500 are always problematic because it's not low volume, it's not high volume. Like mid-hundreds is always a painful threshold, and usually you're going to have to deal with a lot of the MOQ headaches if you're producing kind of mid-hundreds of something. Second sourcing is another thing you need to pay attention to. Now, obviously, you're not going to buy, an Intel CPU from AMD. I say that, but when I was giving the first version of this deck, I said, oh, you're not going to buy, ARM processors from Microchip. But then Microchip bought out Atmel, which does ARM chips. And given that everybody's buying each other these days, what I'm trying to say is, like, you want to make sure that the components that you pick can be bought from another supplier. Now, in the context of capacitors and resistors and that kind of stuff, it's super easy because you just specify what sort of resistance it has, tolerance, what chemistry it has, what package it has, what voltage rating it has, and usually in most cases you just let the CEM source them for you. In most cases they will have them in stock already, and they might even give them to you for free. They're called jelly bean components. But again, if you're using a specific processor, a specific chip, you need to ensure that that part is not going to become obsolete in the near future. This does require a bit of research, sort of keeping your ear on the ground and talking to people and talking to FAEs or reps. And you also need to ensure that the lead times for these parts, specific parts that you're picking, you can't second source, are not going to kill the entire project. You might find yourself, needing, say, 5,000 components, and the distributor inventory only has like 3,000. You call up the manufacturer, and they say, "Oh, okay, yeah, we'll sell them to you, but you'll get them in 52 weeks." The reason I'm obsessed with the whole 52 weeks thing is it actually happened to me. I picked a microcontroller, super confident that it will be available, and then when we got to the stage of actually manufacturing, they're like, "Oh yeah, you need to wait 52 weeks." I was like, can't really do that. We actually had to change the processor on that part, on that design. So lead times can be killer, especially if you're bootstrapped, if you're a startup. It is quite difficult. The other thing is logistics, and this is not just shipping. For instance, if you're buying parts from DigiKey is based in the States, and if that part happens to have any crypto functions in it, you need to fill out a form basically saying you're not a terrorist. Which is funny. My name's Omer, and I usually have a beard, so I thought it was personal at some point, but turns out everybody has to do this. And customs can really slow things down. If you're dealing with Chinese customs, they're 99% of the time super efficient, but come busy shopping periods or the Singles Day that happened like last week, things get really messy. And last point, which also is perhaps the most important point, is fake silicon is a very real problem. It's been found, fake silicon chips, rebadged chips, or simply parts that were not what the package or writing on the package said, have been found in military and medical applications. It's not really scaremongering, like it is just a real issue that happens. Now this could happen for a multitude of reasons. It could be the case that, you know, the supplier just, you know, decided to repackage or just erase the label, or just basically mistakenly or, you know, mistakenly labeled a lower grade part as a higher grade part. It could be empty packages, like you could expect to get a microcontroller in a, like a TKFP package, and you might find that, well, it's just a package, nothing is inside. It's, you know, these things are real. Google for some horror stories, that's really funny. I mean, I wouldn't want to be the engineer dealing with those, but like it's just insane. Okay, enough about components, you know, selection, you know, design, etc. At the end of your, or towards the end of your initial, you know, design efforts, you end up with what's known as a bill of materials. Now, this is perhaps the most important, from the electronic standpoint, this is perhaps the most important document that you'll produce. This is a list of all the parts that you have in your design, quantities, descriptors or idents on the PCB, values, manufacturer, part number, package, order number from a vendor that you might be using, and notes. Now, going back to the whole second sourcing thing, you might see some line items having just generic and just specs. Those are, again, capacitors and resistors. In this instance, I just wanted the CM to source them for us because, and in the end, they just, you know, gave them to us for free because they happen to have some reals. They're really, you know, insignificant costs. If you're working with a lot of projects, if you're working with, let's say, 10 designs that are, you know, sort of similar, share parts, etc., this might be the point in which you look into employing or borrowing some, you know, facilities or concepts from, you know, what's known as PLM systems, product lifecycle management systems, and BOM management systems. So what that simply means is, if you have 100 nanofarads, like 0603 10-volt capacitor, you assign a part number to that. It will be your internal part number, and all designs that need that particular 100 nano cap just use that part number. What that allows you to do is, instead of having to manage different, you know, sources, suppliers, etc. for each project, you could consolidate all that into a single part number, which means you have much bigger buying power, hence better price, and it just makes your life easy. So PLM systems are super complicated, super expensive and horrible, but, you know, borrowing some concepts from them, and the key one really is BOM management systems, and, you know, setting up your own library of components that you'll use and so on, is really, really useful. Now, starting with the next slide, I'm going to start going through a little quicker because we're getting to a stage where, you know, we just covered the fundamental, you know, the process and, you know, the components. So the next couple of slides are specifically for circuit boards and, you know, how you test things and so on. And the reason I'm going to start speeding through is I want to have some time for questions at the end of the session. But if you're going too fast, just, you know, somebody point at me and I'll slow down. So components, we discussed them. The next important factor, obviously, when designing a hardware product is the circuit board. Circuit board is just great, beautiful process of laminating fiberglass, you know, with photoresist and copper layers and electroplating, and there's real hardcore chemistry going on there. And, you know, this is a multi-layer board. It's not a 4-layer board, it's quite a few more layers. As you can see, each copper layer, you know, signifies, you know, well, a layer. And you can see that this is called a via. It goes from the top of the board to the bottom of the board, you know, another one there. If you're interested in this process, and you know, if you're designing or if you're interested in designing electronics, I highly recommend that you get a really good understanding of the circuit boards, because it kind of informs you what you can do with them. You can do a lot of like magical things with circuit boards, but you also need to know the limitations of the process. So this is a very good half an hour or so kind of, you know, it's an infomercial kind of thing for a PCB provider, but it's actually super informative. So check that A couple of notes on PCBs. We'll talk about DFM in great detail. Again, it stands for Design for Manufacturability, but when you're designing a PCB, you really need to pay attention to the footprints that you have, because it might look nice on the screen, it might look okay on the screen, but there are certain things like manufacturing tolerances. The two things can only be so close to each other without any potential short circuits happening. Or you might design beautiful graphics on your circuit board only to find out that they're actually printed by the equivalent of a 150 DPI inkjet printer and so on. So, what you see on the screen is not necessarily what you get out of the process. Mirrored footprints, this is, if you're an electronics engineer, you would have done this. Like this happens all the time. And, again, taking a step aside a little bit, prototyping is very error prone. Like, I'll show you a couple of pictures later, but you're not going to get it right the first time. Nobody does. For a commercial product to be on revision, circuit board revision 5, 6, 7 at the end of the design cycle, that's actually fairly normal. So, and you actually account for that, as part of the development flow. The minimum you would account for is usually 3. So, if it's not great, perfect the first time, don't blame yourself. It just happens in the industry as well. Spacing clearances, we kind of touched on this. The manufacturing process is all about chemical etching, electroplating, and all that stuff. So things can go wrong. There are certain parameters you need to respect, and never push those limits. Like if they say, oh, like track to track width can be 8 mil, or like 6 mil or whatever, don't make it 6 mil if you have like 2 inches on each side. Just like separate them. They don't need to be so close unless they're differential signals or they have special requirements. Also, when you're manufacturing something, you're not going to be designing just one circuit board. So you need to panelize all these things to exist in a much larger configuration. And the next thing, of course, and it's very easy to forget this, is fiducials, which are little marks on the board that allows the little robots to coordinate themselves. They're like an indexing system. So this is at the end of your design, PCB design cycle, you end up with what's known as Gerber files. Gerber files are ancient technology files that talk about apertures, because this used to be actually flashing of like actual physical apertures through like templates and so on. Every copper layer, every solder mask layer, every silkscreen layer, you can see them over here, has a Gerber file associated with it. And never ever trust the output of your circuit software or PCB CAD software, because you need to check it with a Gerber software, because output generation is always problematic. No matter how much your tool costs, you will always find errors in your generated Gerbers. Now, more recently, a lot of the PCB CAD tools are now allowing you to do 3D models or import 3D models into your circuit boards as well. This allows you to really quickly verify whether things fit. Obviously, you need to ensure that the 3D model you're using for the part is actually indicative of the real size of the component, so that's another factor you need to check. But it's usually, like when you actually pay a bit of attention to your libraries, it's really a great tool. Again, it's even available in the open source KiCad that is becoming very popular, replacing the Eagle software that was recently bought out by Autodesk. So if you're at all interested in PCBs, learning PCBs, look at KiCad and look at all the 3D features it has. It's really great, and it's open source. At the end of the process of having gone through schematic capture, PCB layout, you end up with a README file effectively. And this is where you make a note of all the design-specific things you have. One example, I'm not going to read the entire thing, but I added a note saying, please enlarge solder mask pads to fit your clearances as necessary. So if you go back to the Gerber, the green layer you see is actually the solder mask layer covering the copper, right? And the yellow bits you see are copper pads. And you'll notice that there's always a clearance between the green layer and the yellow layer. Not the greatest choice of colors, I do apologize on the presentation, but the reason for that is the solder mask layer it's a silkscreen process, and just some green or whatever color goop is added on there and just squeegees through. The alignment may not be perfect. So if the alignment is not perfect, then what you'll end up with is covered pads. If the pad is covered, you can't solder to it. So that note is just a reminder to the engineer responsible for getting this into manufacture that if you notice that the solder mask openings are not good enough, please enlarge them so that I have working boards, please. Again, so as I've said, I'm not a mechanical person. In this project, I work with an external mechanical designer, an industrial designer, who designed the case for this. This is quite a bit of a push and pull because you need to obviously ensure that the case you're designing, can accommodate the circuit board you're designing, and vice versa. The components you're using on the circuit board fits in the case that's designed for this. So modern tools have beautiful facilities allowing you to, collaboratively design things. But in most cases, it's just exporting the PCB as a step file, as a 3D representation, and just sending it to the mechanical engineer saying, does this fit? Does it fit now? I moved it 1 millimeter. Does it fit now? So it's a painful process if you don't have automation tools in place. Now, you might have noticed we've been talking a lot about like documentation and specs, files, schematics, whatever. Usually when I talk to hardware people about this and say, use Git, they don't get it, but I guess I don't have to talk about Git at all. Version control is crucial, especially when you're releasing data packs. Effectively, a release or a tag of your design to go to the manufacturer, to be manufactured. Now, another thing that differs greatly, and we touched upon this at the beginning of this talk, is that iteration cycles are quite different in hardware. A usual, hardware board spin is around 2 weeks, and that's optimistic. Of course, you can get things faster, but they cost a lot of money. You can get next-day circuit boards, but they'll cost 10 times the standard cost of it. So usually you account for 2 to 3 weeks for each, hardware iteration. And, as I've said, you never get things right the first time. So this was the revision 0 of this board that we were designing. And actually, can anybody tell me what's wrong with this? Hint, look at the pads. Well, if you look at these pads, for instance, you'll see, silver being, distinctly visible. Whereas if you look at these pads, and there's 1, 2, 3, 4, 5, 6, 7, 8 of these. I actually, when I was designing the footprint, I forgot to add the solder mask openings. So the solder mask, the green, basically the thing that prevents things from, solder from sticking to copper, they just didn't put them on because I missed them and the engineer who was processing my file missed them. Things like this happen all the time. Again, if you're just starting out, if you're just sending boards out, if the first revision of your board doesn't work, hey, don't feel bad, it's okay. So when you receive the prototype, you sit down, you solder it. This is the most fun part because your heart is racing, you don't know if it's gonna work or not. And then you start testing things. You find that, this super clever trick I thought would work, but it doesn't work, there's spikes and so on. So this is an iterative process. You might go through this 3 times, 4 times, 5 times if necessary. In parallel, you will start receiving the mechanical prototypes. These are 3D printed plastics that we have received. And the moment of truth is when you actually put the circuit board inside the mechanical case and see if it fits or not. So at this point, we've actually reached the engineering prototyping stage. And this is the point in which you start talking to the contract electronics manufacturer. This is the point where you also start thinking about, okay, I designed this thing, but is it manufacturable? We covered most of these. So, for instance, if you have silk screen or solder mask covering the pads, and this is a pad, the silver thing is the copper that's plated with some solder, and you'll see the text is actually running over it. Now that will actually reduce solderability, and you might have yield issues. Or you might have forgotten to put some fiducials on the board. This is the view from the pick-and-place machine. You'll see that there's some machine vision, AI, machine learning, no, it's just image processing going on that allows the machine to orient itself so that it knows where to place your components. Again, we talked a bit about this. You're not going to manufacture one of your circuit boards, most likely. You need to panelize this. These two are really incredible videos. They're like an hour long each or something along the lines of that, but they tell you the whole process of how you need to think about panelization. And in most cases, your CM will guide you because they will have preferred configurations or preferred sizes for panels and so on. The other thing is, if you're again doing a one-off thing, you could just solder wires to it, test things, put a probe on it, put a scope on it. The more you automate the testing, the cheaper your product is going to be. It's as simple as that. So you might even want to employ on the panel configuration that you have some facility to test all the boards at once. So JTAG is a protocol that supports this. You can chain processors or FPGAs or even memory that supports it together. Or you could go to, or you could decide to do your own thing. You could provide power to all the boards through these little tiny, things. Again, watch the video. It talks about this in great detail. The reason I'm saying go watch the video is these are whole subjects to cover in several hours on their own, and we are running out of time. So the other thing, of course, is testing requires, again, things to happen quickly. So the blue thing, let's say this is the board that you've designed, you might also need to design test jigs to, so that you can simply just plop the, the device on the test on it and then get it tested quickly. Most manufacturing jigs are a lot more complex than that. They have handles, you just push it down, and they're just beautiful. If you search for manufacturing jigs, it's just a whole world of engineering porn, basically. It's just incredible. So the other thing you need to do sometimes is for certain applications, you might have to develop custom test apparatus or custom testers. This, again, the whole purpose of the whole DFM thing is A, so that your design is manufacturable, and B, it costs you not a great deal to manufacture it. In this instance, this was like a little current tester, and these are reference current boards that are exactly the shape of this, so it can quickly be plugged in, which is a lot quicker than having to wire things in and so on. Once you have your data pack ready, you'll be sending this to your contract electronics manufacturer, all the files we've discussed, and then the CEM talks begin. Everything starts with volume. Again, if you're producing 100 of something, that's a completely different picture than producing 1,000,000 of something, right? So depending on your production forecast, sort of the timelines when you need these things, you need to think about material and component sourcing. This goes back to lead times and tooling schedules. Again, back of this, tooling 8-10 weeks. It's a long process, and MOQs as well, minimum order quantities for the products. The second one is the technical process, which starts with DFM. You need to think about how you're going to automate the manufacturing, testing, and everything, to make sure, as minimal human touch is required for your products. And also, how are you going to manage quality, yield, and ensure that, environmental factors or requirements are met. And of course, financial, again, this is a whole complete, presentation on its own, but what I will say is if you're dealing with a contract electronics manufacturer, go for or demand open book pricing so that you can see clearly how much things cost, what their margins are, and just so you have a clear and open communication channel with your manufacturer. Now, regulatory and compliance, when you have a product you want to release to the market, depending on what it is, you might have to go through very stringent testing. If you're designing a medical product, obviously this will be much more difficult than, say, you releasing this little clicker thing. But even this, it's wireless, so you need to worry about the safety of your product, the electromagnetic interference that it might create, the RF, radio wave interference it might create. If you have, say, a Wi-Fi device, you need to ensure that it's compatible with the Wi-Fi stack. Or if you're designing a domain-specific, let's say if you're designing an agricultural thing, you need to ensure that the agricultural specification that's required requirements of that are met. So if you get all these right, and if you wait a little bit, you end up with products. And this is actually quite a rewarding feeling. In this instance, I didn't unfortunately have a full shot of all the units in one place, and I was doing some further testing once the products were in. So, but we started with a breadboard prototype, and ultimately we ended up with finished goods that actually went into use and deployed in classrooms and lecture halls. So that's just under 55 minutes. Thank you very much for listening, and if you have any questions, I'll be happy to answer them if I can. Thank you. How are we doing for time? Do we have maybe 5 minutes or so?
some questions.
Yeah, a couple of questions. Nope? Cool. Let's go grab a coffee. Thank you, everybody.